Okay, it's precisely 9. Buenos dias, dzień dobry, good morning. The first speaker of this morning session, plenary speaker, is Łukasz Grabowski from University Leipzig. Let me present in short our speaker career. He began his mathematical career at the University of Szczecin. Szczecin is a town at the northwest corner of Poland. And when he completed his master thesis, but meantime, for 1 or 2 years, he took courses at the University of Warsaw by exchange program. Then he moved to Göttingen, where he did his PhD degree, solving a problem of Michael Atiyah about the realization of Betti numbers in square cohomology, and the positive solution of this conjecture had been done by him. All the numbers could be realized, positive numbers. But what is interesting in his solution is the method in which he, as I understood, he used dynamical random walk of Turing machine, something like that, at least Turing machines, which was unusual. And then he moved to Lancaster, UK, and in the meantime, expanding his mathematical area of activity, which covers also combinatorial metric measure theory, and ring representation of a discrete groups, many other things, and one of the other results for which he is famous is some version of a classical squaring disk Cycle-Tarski problem, which, I mean, they generalize it or expand it or make better, improve Lachkowich's previous result. And this is an article published in the Annals of Mathematics, joined with Andrzej Mate and Oleg Prichurko. Let me add that Andrzej Mate is one of the first winner of this international Banach Prize for young mathematicians of the first edition. Łukasz was not covered, even they didn't work together at that time, because his thesis had been done in Germany, and Germany that was not covered in this program. Okay, we had opportunity to meet in Poznań when Łukasz delivered a special lecture named by Wojtek Polikowski, which is dedicated to young mathematician. And the last fact which I would like to emphasize is that among his current PhD students is one Asturian Spanish mathematician, Jordan Hector Sanchez. So there is also some Spanish accent in his career. Your stage is yours.
Thank you very much for this very nice introduction. Thank you very much for the opportunity for me to give this talk. So let me just start by saying what I'm gonna talk about. So I would like to talk about expanding actions of groups, and the first part is supposed to be a gentle introduction to the definition, to some examples, and the second part and third part are certain chosen applications of this notion of expansion in group actions. This is an extremely biased choice, because these are two applications which are to some small extent involved. But this notion of expanding actions, of expanders, this is an extremely fruitful notions and has many more, much more probably important applications, and therefore this short apology why those two are chosen. It's just two topics which are somehow closest to my heart. Okay, so let's start with expanding actions. So let me tell you what the basic setup here is. X mu is a standard measure space. Examples, especially in this first part, this could be a circle, torus, sphere, Euclidean plane, Euclidean space, with the natural mu, so some form of a Lebesgue measure on those spaces. G is a group, is a locally compact group, but again, we always formulate it in such a great generality, but typically it's just a full group of isometries of X, because X really comes with some sort of a metric, as you see from those examples. So G is either the full group of all isometries or some countable subgroup of isometries generated by finitely many isometries. And then we have a measure preserving action of some sort. So X mu, let's say, example, circle with Lebesgue measure. For G, we could take, this should be SO2, so the group of rotations, or we could take a countable group generated by a single irrational rotation. This would be just an infinite cyclic group. Or we could take G, some countable group generated, for example, by several rational independent rotations, in which case we would be dealing with a copy of Cartesian product of cyclic, infinite cyclic groups. Another example in similar spirit is when we consider X to be the R3 with the Euclidean metric, and G is the group of all isometries of R3. Okay, so these are the examples, and now what does it mean that an action is expanding? So I want to focus on the case of probability measure, just because the definition is slightly easier and quicker to state. So we first assume, but really for the purpose of definitions, this is the only case we will assume. Later I will tell a little bit about how this is modified for the case when the measure is not probability. But for now, we assume that X mu is a standard probability measure space. So let's say this will be this case of a circle or a torus or a sphere. And we say that this action is expanding. So this is really the main notion which I want to talk about. So this is a good time to be focused. We say that the action pi is expanding. This is a probability measure preserving action if we can find a finite set of elements of G and a positive number epsilon, such that for every Borel set U, which is not too big, whose measure is at most 3/4. 3/4 is arbitrary. We can use any number larger than half. So such that for every Borel set whose measure is not too big, we have that if we act on U with the set F, so my notation here, Fu, means that, oh, I'm sorry. My notation here, Fu is just a union over all translates of U by elements of F. So we look at U translated by all the elements of F. This is a set which is typically larger than U. We look at its measure, and its measure should be multiplicatively more than the measure of the original set. It's not just a little bit bigger, or depending on the sets. It really there should be always, no matter what u we take, there should be this multiplicative factor here. Okay. Okay. So that's the end of the definition. That's what it means for an action. This is what it means for an action to be expanding. Let me give you, just because it's such an important definition for us and to get more accustomed with it, let me sort of just rephrase it in case it's more palatable this way. So in other words, we can phrase it the following way. Let's say that we have this sequence of Borel sets, U1, U2, and so on. And what does it mean for them to be almost F invariant? So if there was no almost, then F invariant would be just that every element of F just preserves every set. But what does it mean almost that this sequence is almost F invariant? Well, let's assume that those sets are not too big. And crucially, we assume that they are more and more invariant. So the measure of Fu I, the limit should be with respect to I here. So the measure of Fui should be roughly the same as measure of as the measure of Ui. So this is what it means for a sequence of sets to be almost F invariant. And with this definition, we can rephrase the property of expansions as follows. We say that the action is expanding if we can find a finite set of group elements such that there are no almost F invariant sets. This is a very classical property. I don't know who studied it first, but it goes to prehistory of ergodic theory. Some names are Feldman, Moore, Kohn, Weiss, but this might have been even known to Banach and Tarski. I don't know. This is a very natural property to study. And it has an equivalent formulation in terms of a spectral gap of certain operator. So I want to mention it basically for completeness. I'm not going to use this here, but when you want to establish this property of expansion, in all cases that I'm aware of, you actually would use this spectral gap condition. So let's quickly just state it. In our situation, we have x with a measure, so we can consider L2 functions on x, and we can consider the averaging operator, Tf, associated to our finite set of group elements, which is defined as follows. If we plug a function, small f, to Tf, then it should output another function whose value on x is the average of the original functions with respect to those group elements in this set F. And then the spectral Gankow condition is that this averaging operator should have a norm which is strictly less than 1. Okay, so expansion is equivalent to this kind of conditions, but I'm really mostly, for applications, I'm really mostly interested in this nice condition directly in terms of expansion.
Excuse me, what does it mean? G in -1 dot x?
Lower dot, I'm sorry, I should have said this. For me, lower dot always denotes the action. So we have this action pi, and I would, instead of writing, let's say, pi of g of x, I would write g lower dot x. So lower dot x is one of the fairly standard notations for group actions, and I usually use this notation. Okay, so let's see some examples of expanding and non-expanding actions. So first, for non-expanding actions, an example of non-expanding actions is given, for example, by amenable groups. I will say what an amenable group is in a moment. Let me start by saying that if G is a countable amenable group, then every action is non-expanding. So if you are interested in this property, you will not find any examples among those groups. So let's say groups like Z, Z squared, and so on. Important groups, solvable groups, these are not good. Why such an action is non-expanding? At least when the action is free, this follows from a standard tool of ergodic theory called Rocklin's lemma. In particular, Rocklin's lemma is usually stated for one transformation in some elementary courses, but there is an extension of Rocklin's lemma to arbitrary amenable groups due to Ornstein and Weiss. And let's discuss it a little bit. What does this Ornstein-Weiss lemma say? It says that we can almost tile the orbits of the action with Fellner sets, and we can do it in a Borel way. So I want to state it in this informal way because this is how I think about this lemma, but I understand that this statement is, if you are not familiar with this topic, probably just completely meaningless. Nevertheless, I want to start with this statement because this is how I think about it. But let's now discuss it in some more detail to give it a little bit more mathematical substance if you are not familiar with this. So first, what does it mean for a finitely generated group G generated by some set F to be amenable? That means that there exists a sequence of Fellner sets. This means that there are finite sets F1, F2, there should be 3 dots there, so F3, F4, and so on, of G, such that they are almost invariant with respect to multiplication by capital F. So here, capital F and I, this would be again all the products of element of F by element of Fi. And if this quotient is 1, this means that capital Fi is almost invariant with respect to multiplication by F. So that's the end of the definition of amenable groups. Amenable group, you need to have this kind of sequence. What are examples? Cartesian products of Z. More generally, and with the essentially same proof, groups of sub-exponential growth, solvable groups, which include some groups which are not of sub-exponential growth. Now we can state this Ornstein-Weiss lemma in a precise fashion. So suppose that we have our amenable group, G acting on X. So G acting on X is a PMP probability measure presenting action of an amenable group. Then, for every epsilon positive and every Fellner sequence, we can find a Borel set S in X and the Borel function on this set, such that for S and T different elements in S, we have that if we act on those elements with Fellner sets, then we get disjoint sets. And furthermore, the measure of the set of all translates by Fellner sets is large. This is slightly too technical to understand in this kind of talk. So let me draw you a picture about what Ornstein-Weiss says. So first of all, what is a Fellner set? This is supposed to be a K graph. This grid is supposed to be the K graph of the square of the group Z squared. And I just draw here a large square of size n by n. And I want to say that this is an example of a Fellner set, meaning that this set is almost invariant with respect to multiplication by the set F of generators of the group. Indeed, we see that the boundary of this square has roughly 4n elements. The set itself has, it should be n squared, I'm sorry. This should be n squared. So the boundary of the set has 4n elements. The set itself has n squared elements. So n times n has n squared plus 4n elements. So we see that f times n divided by fn is roughly 1. So these such squares will be an example of a Fellner set. This shows that this group is amenable. As I said, the same kind of idea constructs Fellner sets in group of sub-exponential growth. But let's now see what does Ornstein-Weiss say. So what is this picture here? So now the grid is no longer a K graph, but rather I fix a point in my probability measure space on which we have. Let's say this is a fixed point, and then it should be on the grid. So let me choose this point. This point looks more like it is on the grid. So then the grid itself is the orbit, is the orbit of the action, right? So this still looks like a K graph, but now I'm looking at this on the space on which we act. And then Ornstein-Weiss says that essentially we can tie the whole orbit with some squares or rectangles. There will be a small amount of points which are not covered, but almost all is as good as I want it to be. Almost all of the points are covered in with those squares. And then to get almost invariant sets, I would just choose roughly half of those squares, which gives me roughly half of the orbit. So this will give me a set which has small boundary, showing that we have almost invariant sets. Okay, so this is an argument which shows that amenable groups always act in such a way that there are almost invariant sets, because we see those Fellner sets in the orbits, and we can always, in some Borel way, choose roughly half of them. But amenable groups, if we talk about expansions, as we just saw, are slightly uninteresting. They just don't provide us with any examples of expanding actions. What about free groups? Well, it turns out that free groups have both expanding and non-expanding actions. So first, there is a general statement, general characterization of non-amenability, which is as follows. Every countable non-amenable group has some free probability measure presenting action which is expanding. So amenable groups never have expanding actions, and non-amenable groups have at least one such action. If you want an example, this would be an example of slightly different sort than action on a circle or action on a torus. This would be acting on a counter set. So G acts on infinite product of two element sets with just a product measure. So this works for any non-amenable group. In particular, this works for the free group. So in particular, we see that free group on two or more generators has some expanding actions. But it turns out that free group F2 also has free non-expanding actions. So you could think that maybe free group is sort of as non-amenable as possible, but this is just not true. How could we construct a non-expanding action? We could start with any action of F2 on X, and then we could take a non-free action of F2 on Y, which factors through an action of an amenable group. So for example, it factors through an action of Z. So we know that the action of F2 on Y, this is a non-free action with huge stabilizers, but this action on Y is definitely non-expanding, because it factors through this action of an amenable group. And then it's easy to see that in this situation, when at least one of the factors is non-expanding, we deduce that also action on the product is non-expanding, and this action is free. So the orbits really look like copies of F2, and yet we can somehow find expanding sets, non-expanding sets in small boundary. So perhaps this is something which you can now be a little bit surprised by. Because what is our situation? We just found by very general means an action of F2 which is non-expanding. So it means that if I draw an orbit in the tree, so if I draw an orbit, I see a tree in this action, and somehow there should be some sets with small boundary there. So can we see what those sets are? Yes, we can. We used to. Oh, I'm so sorry. So one picture is missing. So I will just. So can we draw those almost invariant sets? Yes, and this is left as an exercise. So it's very it's a very nice fulfilling exercise to understand the orbits of such a non-expanding actions and to understand the sets with small boundary which exist on a tree. And this is a wrong picture, so let's move on. So now we had those amenable groups which never have any expansion. We have groups like free groups which sometimes have expansion, and then very interesting case of expanding actions comes from groups with property T. So I don't want to repeat the somebody will have to solve the exercise now. So I don't want to repeat the definition which Piotr Nowak gave, and my reason is that I have my favorite definition. So as I get older, I stop believing in things like unitary dual or Feld topology on the space. I need like a number, basically less than 1,000 to be able to assume that something exists. So here's a definition of property T for a group which I like. The statement is this is equivalent to any of the definitions which Piotr Nowak was saying last time. Is called Conway's theorem. So we say that G, a countable group, has T, that's property T, if every ergodic probability measure representing action is expanding. So this ergodic means just that there are no invariant sets, right? So invariant set has to have measure 0 or 1. That's what ergodic is. If an action is expanding, then it better be ergodic, right? If we have an invariant set, then certainly this set does not expand. So G has T if every ergodic probability measure representing action is expanding. Essentially, every action is expanding. Every ergodic action is expanding. What are examples? Just like we saw in Piotr's lecture, SL3Z is an example. Other lattices in higher rank groups are also an example. So we have, again, amenable, no expanding actions, property T, only expanding actions, and everything in between. Some actions will be expanding, some actions will be non-expanding. Okay, so what are less abstract, less general expanding actions, sort of expanding actions in nature, if you will? So first of all, establishing that an action is expanding usually is hard, and it always uses harmonic analysis and establishing that the norm of this averaging operator is less than 1. The first sort of natural example which I know of is the action of SL2Z on the torus. So torus is the quotient of R squared by Z squared. So we have action of SL2Z. And Rosenblatt in the 80s showed that this action indeed is expanding. The action by isometries, by rotations on the sphere, this also goes back to the 80s. First, Margulis showed that those actions are expanding in dimension at least 5. And this, in fact, he did it by finding subgroups with property T is in S of 5, SON and higher N. so that he did not have to care about specific properties of this action. And it took few years to prove that those actions on two, this should be 2, 3, 4, so 2-dimensional, 3-dimensional, 4-dimensional spheres are also expanding. And in particular, you cannot use property T there. You have to again use harmonic analysis sort of directly by understanding spherical harmonics on the sphere. But okay, we have those results. These are nice classical results. Let me just say that this topic, although it started quite a long time ago, this is still active. People still try to understand which groups of isometries give you expansion on the sphere. Fairly recent result by Burger and Gabut is that basically every dense subgroup of SON, as long as the matrices have algebraic entries, have expansion. Okay, so that was my short introduction to the notion of expansion and to examples. Now I would like to say something about those applications. So we can use this expansion to prove theorems which sometimes actually don't even look like they have anything to do with expansion with ergodic theory. First is matchings at equidecompositions. Let me start by reminding you what is the Hall's theorem in finite graphs. So this is just a theorem which you learn when you go to some kind of an introductory graph theory course. We start with a bipartite graph with parts A and B. That means that we have a set of vertices A, set of vertices B, and all the edges go only between A and B. And we would like, what is that we are after? We would like to find bijection between A and B, which is given by the edges. So the if and only if condition is as follows: suppose that every set of vertices K, which is entirely in one part, have more neighbors. N of K is the neighbors. Then the set has members itself. So cardinality of the set of members should be at least equal to cardinality of the set of vertices. You see, this is you should think of this as sort of an expansion condition. And if this is the case, then there exists a perfect matching. So we can choose a set of edges between parts A and B, which implement a bijection between those parts. I want to tell you an algorithmic proof of this theorem. How do we construct a matching here? First, take some matching. So take some set of edges which implement some injection between the parts. And then there's a notion of augmenting path, which I will define in a moment. I will just finish this algorithm. So whenever we see an augmenting path, starting from short augmenting path to long augmenting path, we flip them, and that's it. Okay, so the algorithm is very simple as soon as we understand what are those augmenting paths. So here I have, I want to explain it by example. So my edges, which are in the matching, so in the algorithm, we have some matching. This is part A. This is part A, this is part B. And both dotted and solid lines represent edges of the graph. But now we have some injection from, let's say, we think of this as injection from A to B. These are the solid lines. We have a partial matching. But maybe we have an augmenting path. So what is an augmenting path? It starts with an unmatched vertex, and then it goes through unmatched edge, then matched, unmatched, matched, unmatched, matched, unmatched, and it should end in an unmatched vertex. So when we see such a path, we can flip this path, meaning that instead of taking this injection, we take the injection given by the dotted edges. And if we flip, then certainly the number of edges which are matched, the number of vertices which are matched now is larger, because both this vertex and this vertex will be now matched. And it is not difficult to see that this simple algorithm which I described really works and gives you eventually a matching. So again, you start with any matching, and then when you see an opportunity to improve your matching through augmenting paths, you just do it. And you do it first for paths of length 3, then length 5, length 7, length 9, and so on. And you prove that if you flip paths of length n, then it does not create any augmenting paths of small length. So by the fact that the graph is finite, this really has to converge to a perfect matching. Okay, and why is it that I talk about this? So there is a theorem of Lyons and Nazarov, which can be described as Hall's theorem when we have expansion. So let's set the stage here. So suppose now that we have a PMP action, probability measure presenting action of a countable group. So this kind of situation which we had in the basic setup. And suppose that we have a finite set, so just like before. And suppose that this is a typo. This should be A and B are A and B are subset of X. This should be A and B are subset of X. These are disjoint Borel sets. So we have an action, finite set of group elements, and two sets which are disjoint. This should be thought of as my parts in the graph. And we consider again a bipartite graph. Now the vertex set is huge. It is this Borel set, this joint union of A and B. And we so this is the vertex set, and how are the vertices defined? So we say that small a, small b is an edge whenever b is an image of a under some element from our finite set F. So we have those set A's and B, finite set isometries, and we send A, capital A to B whenever it makes sense. And these are our edges. So, so now the question would be whether we can find not only a matching in this graph, because actually the whole condition, if you are just interested in the matching, that it works just like before, it's still an if and only if condition. But the interesting question is whether we can find a Borel matching. So whether we can find a nice matching if you want. And we have a very nice analog of Hall's theorem due to Lyons and Nazarov, which is as follows. Suppose that we have an expansion. So suppose there exists some constant epsilon greater than 0, such that for every Borel set of vertices k, which is entirely in one part, just like in Hall's theorem, now we have that measure of the set of neighbors is at least multiplicative factor larger than the measure of the vertices. So in Hall's theorem, we had just cardinality of n of k is greater or equal to cardinality of k. Here we need expansion. So not just greater or equal, but the measure has to expand. The set of vertices has to expand. And then the claim that there is a Borel perfect matching, possibly after discarding some set of measure 0, which in this talk I don't care about sets of measure 0. Okay, so let me finally try to give you an idea how expansion of those groups actions, or expansion in the sense of Lyons and Nazarov here, is used in proofs. So this is an example application. So the point is this: we repeat exactly the same algorithm as for the Hall's theorem. So we start with some matching, could be an empty matching, and then whenever if we see augmenting paths of length 3, then we just add then we just flip them. And then we see some augmenting paths of length 5, we flip them again, and so on. So we repeat exactly the same algorithm. It makes sense to do it in a Borel fashion. There is absolutely no problems there. This way, we do get a sequence of Borel matchings, maybe not perfect yet. So we get a sequence of Borel matchings. Clearly, the set of unmatched vertices is as small as we want, so that's great. But what is the potential problem? The main issue is whether those matchings stabilize, right? Because when we keep flipping the edges and we have to do it really infinitely many times, then the danger is that we will keep flipping every edge infinitely many times, and this will never stabilize to anything. So the idea is to use expansion to show that, in fact, edges will not be flipped too many times. And the reason why expansion helps here is explained on this picture. Okay, so I'll try to describe what we see on the picture. So suppose, let's say, ignore the sentences which are under the picture. Let's focus on this picture. So we have part A and part B. And suppose that unmatched vertices are in the set of measure delta in A. This is all my unmatched vertices. These are unmatched. So how? Let's see how long do I need to have augmenting paths to start covering those vertices. So if I start building augmenting paths, then whenever I go to the right side, I expand by 1 plus epsilon multiplicatively. So I start with this small set of unmatched vertices delta. I go to the right side, now I'm 1 plus epsilon delta. Okay, then I go back to the side A. I don't expand this way because I go through this injection which already I have established, but then when I go to B again, then I again expand by multiplicative factor. So what this means is that if we don't see any augmenting paths of, okay, so this way you see that we will very soon cover more than half of B. And then I can start doing this procedure also from B, from some unmatched vertices on B, and very soon after log 1 divided by delta steps, I will start seeing half of A as well. So those sets will intersect. This means that thanks to expansion, we have this first sentence. So if we don't see any augmenting path of length roughly log of 1 divided by delta, then it means that we are already quite good. Then it means that the measure of unmatched vertices has to be at most delta. But that means that when we flip augmenting paths of some length n, we flip at most n divided by 2 to the power n edges. But this is a summable series. This means very easily by Borel-Cantelli type argument that indeed every edge almost surely flips only finitely many times. So I like this argument very much because we see very directly how expansion helps us to establish something interesting. Okay, this level. Sorry. Okay, so let's see now how Lyon's Nazarov theorem allows us to obtain results about measurable equidecomposition in this talk, at least up to measure 0. So we say that two sets A and B are measurably equidecomposable if there exists a Borel partition of A into finitely many Borel sets, disjoint sets. This equal with mu means that we only care about things up to measure 0. And isometry is gamma 1 up to gamma n, such that B is decomposed by images of the parts of A. So we have set A, set B, we partition A into finitely many pieces, we move those pieces by isometries, we should obtain B. And then we have the following theorem, which is as follows: if A and B are subset of R3 bounded of the same measure and they have non-empty interiors, then in fact we can find a measurable equidecomposition. And I should say that many improvements were made to this theorem. This is a very popular area of study. Also, we didn't start this area of study, so our theorem was also an improvement to some previous results. Some names are important names are Marx Underger, who managed to prove a similar theorem just with Borel pieces, Cieśla, Sabok, Kuhn, and especially recently there was an article which gained some traction in popular science journals by Matte-Noel and Pikurko, when they show that in this kind of theorems we can take even sets which are very simple in the Borel hierarchy, just Boolean combinations of F sigma sets. Okay, so how do we prove this kinds of theorem? Well, we find this finite set of isometries between A and B such that the expansion assumption of Lyons-Nazarov are fulfilled, and then we use Lyons-Nazarov. This is in fact possible in greater generality than for sets with non-empty interiors, and I find this quite interesting because it leads to some interesting open questions. So let me briefly tell you about this greater generality. We can say that a set A in R3 is a domain of expansion. So this is this situation, which is important, for example, when we don't have probability measure. Now we restrict attention to a certain set A, and we say that essentially the group action expands in this set. So we say that A is a domain of expansion if there exists a finite set F of isometries such that for every Borel set U, which is not too big, we have that if we act on this set U and we intersect back in A, then we have expansion. So U does not just expand in R3, but it really expands in this set A. And then more general theorem is as follows. If A and B are two bounded domains of expansion of the same measure, which cover each other, which means that if I have A and B, I can cover B with copies of A, and I cover A with copies of B, then A and B are measurably equidecomposable. Why did I decide to talk about this slightly more general version? I had to add an extra definition of domains of expansion. So this is because it is interesting to ask whether, if I have, let's say, two compact sets in R3, then whether it is possible to decide in some way, which needs to be always defined, to decide whether those sets are equidecomposable. And by this theorem, the answer would be yes, if, for example, every compact set in R3 was a domain of expansion. So the answer to this question would be yes, if every compact set was a domain of expansion. There was some effort to see which sets of R3 are domains of expansion, and with Matte and Pikurko we found an example of a nowhere dense, so very far away from being with non-empty interior, so nowhere dense set which is a domain of expansion, but together with my former postdoc Tomek Cieśla, we showed that in fact if you cleverly, or let's say fairly cleverly, construct a random compact sets, so if you put some probability measure on compact sets, then almost surely such compact sets will not be domain of expansion. And our construction suggests that maybe this problem to decide whether two compact sets are equidecomposable or not, this problem might be hard. And hard, not just hard to do for mathematicians, but in some precise sense of descriptive set theory, that you can reduce this problem to some hard problem. Okay, how much time do I have?
No, still a little bit, because we took just 5 minutes.
5 minutes? Okay, so yeah, but I think realistically speaking, I will stop here. So the second application is very exciting, but I want to at least mention that this the name. Because this is a topic which I work on together with my PhD student Hector Hartlon Sanchez, who's gonna be on the job market this year. So if you want to know more about this topic, it's a great opportunity to invite him for a talk or talk to him. So yes, I think I'm gonna stop here.
Thank you very much. Oh, yes, it works. Question, comments, as usual.
I have a very simple question. There were some numbers in the theorems, for instance, 3. Should be Rn as well, or 3 is crucial? And the
Do you remember which theorem was it?
The last one.
There was subset of R3. What is the difference between R3 and R4?
No, okay, I see. So
maybe another constant before.
And there was another 3/4.
no, so for 3/4, I said explicitly that you can, for 3/4, you can say any constant at least 1/2. So you need to fix a constant,
Okay.
but it has to be 3/4. Whereas here, it's just a shorthand for writing Rn, where n is at least 3. So the situation is different in R2, but from R3 onwards, the situation is the same for the purpose of those theorems.
Any more questions? We need microphone.
Thank you for a very nice talk. So I'm interested in the settings related to modular forms. So for example, we have action of SL to Z on upper half plane, or the action of congruent subgroups, or maybe the actions of symplectic matrices or generalized upper half planes and so on. So I don't work in these settings, and I'm not sure where it makes sense to ask these questions. But for example, with this hyperbolic matrix, does it make sense to speak of, is there a notion of domain of expansion? Is there something, are there theorems related to this equity composability and so on?
Yes, definitely. To be honest, in the paper, I believe that we have also a result for hyperbolic plane and action by isometries by hyperbolic isometries, but we have the result only in the sense that we quote known results about expansion of this action by isometries. So yeah, I would say that in the hyperbolic geometry, it's even easier for sets to expand than on the Euclidean plane. So if we focus on this particular question, whether we have equity compositions in hyperbolic geometry, then yes, the answer is definitely yes. Then there are some other actions which are sort of number theoretic origin, which again, I mean, I don't work in this, but you can construct certain profinite actions which will have expansion property by deep, because of some deep number theoretic results, some Selberg theorem on stuff. So yes, certainly in this sense also, I would say that there are positive results in the sense that number theory very frequently has established spectral gaps, and therefore you can translate it to expansion, although the space will not be any kind of natural, like geometric, it will be more like a profinite limit of spaces, profinite space.
Thank you.
Thank you. Any more? Yeah. 3 minutes. If no more questions, thank you very much once more.